Hello everyone, welcome back to my video where I'm doing a series on wireless communication and convergence network for my class, and today we will be discussing introduction to wireless communication. Here in the picture, buildings, vehicles, and smartphones can be observed to be connected to one network. This image represents how network communications will work in the future, and all these connections will be made possible by using IoT. When using IoT, it is possible to create a smart home environment along with smart home furniture, where we can turn lamps on or off, run the bath, and even water the garden from just a click in our smartphone. And on a larger scale, it is also possible to create smart cities, where all buildings are interconnected with one another. Okay, so I've briefly mentioned IoT. So what is IoT? IoT, or short for the Internet of Things, enables every electronic device that has an internet connection to be connected with one another. The electronic devices include smartphones, consumer electronics, cars, lights, sensors, medical devices, and etc. Usually, IoT devices are compact. They consist of a singular or multiple small sensors that are attached to a small CPU with a limited processing capability along with a small battery as a power source. Hence, IoT devices tend to be more efficient in energy as well as efficient in data processing as all their data values are stored in the cloud. However, a downside to IoT devices is that they're not very ergonomic as they are designed for one-time use or deployment. When an IoT device becomes exhausted, they can no longer be used. Here we can see all the wide application of IoT, which include sectors such as basic consumer and home use, smart infrastructure, security and surveillance, healthcare, transportation, retail, industrials, and others. All these devices share a connection to a network. Okay, now we will be discussing the challenges when it comes to implementing wireless communication. So we will first discuss the challenges in terms of the network. The first challenge is gigabyte per second data rates with no errors. It is essential to provide a high-level data rate with a lower number of error percentages since users enjoy the use of high-speed internet, which of course requires a higher data rate. Hence, a higher data rate will produce a higher quality of internet. The second challenge is energy efficiency. It is common for people to use more than one telecommunication device as their daily life often demands it. These devices need to be powered by electricity, which leads to an increase in the usage of electricity resources. So the device, of course, needs to have a higher efficiency rate, such as better battery quality and lifespan. For the third challenge, it is the scarce or bifurcated spectrum. The spectrum wave used for wireless communication is limited as each telecommunication technology is designed for a dedicated spectrum range. For example, FM works in 88 megahertz to 108 megahertz range, while 5G works in 3.3 to 3.8 gigahertz range, and so on. The fourth challenge is reliability and coverage. Reliability is how the system is able to provide a good service. An example of this is how they provide and maintain good data rates, low latency, and etc. Hence, a wider coverage will gain more users. Oh, sorry. Coverage is the amount of area a network is able to cover. Hence, a wider coverage will gain more users. The fifth challenge is heterogeneous networks. A heterogeneous network technology such as um, a heterogeneous a heterogeneous network means that there are a number of different types of network technology such as 3G, 4G, 5G, Wi-Fi, Bluetooth, and etc., all which needs to work flawlessly in one place. The sixth challenge is seamless internet or handoff. Seamless inter-network handoff means the process of sending service to another base transceiver station. This process is essential so that the user is able to call a person seamlessly from areas that are far away without any interruption. This is the challenge that occurs when a user is disconnected from the BTS in the region and is redirected to another one that is near the destination area. Now let's move on to the challenges in terms of device or SoC or system on chips. So the first challenge is the good performance as there are many components of a telecommunication device. For example, in a smartphone, there are components such as Bluetooth module, memory module, CPU, radio module, GPS module, and Wi-Fi module. The smartphone must have a good performance in order to provide a good user experience. The second challenge is complexity. Components inside our smartphone, for example, are getting more and more complicated since the sizes are getting smaller as time goes by. All to give a compact smartphone design with advanced technology to compete in the market. Now, the third one is challenges in size, power, cost, and energy, which are quite self-explanatory. Fourth challenge is high frequencies or millimeter waves. Nowadays, a high data rate is the standard, and it can only be provided with a high frequency. The fifth challenge is multiple antennas. To deliver a high frequency, multiple antennas are needed in one configuration. In the current generation, smartphone uses a 2x2 antenna configuration, which means that there are 4 antennas inside our smartphone. The sixth and final challenge is multi-radio integration and coexistence. It means multi-work frequencies, where our smartphone can be used for radio, Wi-Fi, and GPS. Now, our smartphone still needs to have coexistence with older technology. And an example of this is that our smartphone is a 4G based network, but it should also be able to use 2G and 3G networks. This is another challenge in this era where the airwave spectrum is almost full and delivering high data rates becomes difficult. As you can see, within a mere 5 years, the traffic grew from 100% to 1,250%. We can also see the amount of spectrum is capable of being allocated here in the bottom bit of the graph. So from 2009 to 2014, due to this large amount of mobile data growth, there is a spectrum deficit. In 2009, we have 377 megahertz available for crossover systems mobile devices. But in 2014, there was a massive deficit of negative 275 megahertz. Due to the ever-growing demand for spectrum allocation, it is suggested for the government to manage airwaves so that high data rates are able to pass through with ease. Now we move on to the Shannon theory. So, what is the Shannon theory? The Shannon theory tells the maximum rate at which information can be transmitted over a communications channel of a specified bandwidth in the presence of noise. Or in shorter words, the theory, quantifies information. And the Shannon formula, as you can see below, it describes the information capacity is affected It describes that the information capacity is affected by the SNR and bandwidth, or B. The SNR is affected by the power of the signal and the power of the noise, if you forgot about that. And the amount of information that can be received really depends on the amount of power that is generated by the signals. So when we have a high power, the amount of information that is sent and received becomes greater, and vice versa. The information is also proportional to the bandwidth. When the bandwidth is large, more information can be transferred through compared to when the bandwidth is small or narrow. Now, thanks to the Shannon theorem, we can develop the current communication technology. This formula is still useful until today, or even to 5G and beyond. And one of the big questions is, are we at the Shannon limit of the physical layer? Some experts might agree on on this statement. A few examples of the statements include: the wireless industry has reached the theoretical limit of how fast networks can go by Fisher. And in the second one, we are 99% of the way to the barrier known as Shannon's limit by Warren. But as an opposition, there is no theoretical maximum to the amount of data that can be carried by a radio channel by gas. These statements can be considered to be both correct and incorrect, well, all depending on what side you agree on the most. Well, the truth is we don't know the Shannon capacity of most wireless channels, but if you observe the formula above, the capacity is unlimited as long as there is an infinite source of power from the signal and the noise is capable of being suppressed. The only limitation to this theory is the device, as they all vary in terms of performance, complexity, reliability, and sensitivity. A device is labeled as good when it is capable of detecting the smallest amount of power from the source without the help of an amplifier. The Shannon capacity of most wireless channels depend on many factors, which include time-varying channels, channels with interference or relays, cellular systems, as well as channels with delay, energy, or financial constraints. Time-varying channels means that the channels fluctuate over time. Hence, the signal becomes very unstable. The capacity becomes more challenging to define when there are interference or relays on the channel. In cellular systems, the frequencies are reused to increase the capacity. And finally, channels with delay or energy or financial constraints are, well, self-explanatory. Attempting to build a channel with all those factors can be difficult. In the end, we can apply the Shannon capacity formula as a reference when designing a channel with a fitting performance. Finally, we'll talk about the current and next-gen wireless systems. Today, it is common for a device to be able to cater to 4G LTE cellular systems and even 5G systems. Or maybe in 10 years' time, 6G will be the most common cellular system. In certain countries, the millimeter wave massive MIMO systems have been applied, as well as satellite systems such as Starlink. Wireless systems that might appear in the near future include 5G to 7G Wi-Fi systems, as well as the ad hoc and cognitive radio networks. Energy harvesting systems are also an emerging system in which the energy is not sourced from a battery, but sourced by harvesting through a mechanical system, such as a turbine system, to generate electricity for the wireless communication system. And an unorthodox example of an emerging system includes a power source from chemical or molecular system, which indeed still has room for development and innovation. Okay, thank you everyone for tuning in, and I'll see you all next week where I will discuss signal propagation and path loss models. Have a good day, everyone.